This is a set of preset dropping angle scales for use with the Norden bombsight. They are relatively uncommon and can be difficult to find. To understand their purpose, it is useful to review the math and trigonometry used by the Norden bombsight to help calculate the tangent of the dropping angle. These scales are used with the E6B flight computer. There can be quite a number of calculations involving a math and trigonometry involved in determining the Norden bombsight dropping angle. For a more complete explanation of this, you may wish to view the YouTube video Norden bombsight tutorial. As a brief review, one side of a right angle triangle is formed here by the altitude, here in the red. The altitude and speed determine the actual time of fall that takes the bomb to strike the surface. The time of fall times the ground speed of the airplane yields the whole range, seen here in the blue. The distance that the bomb will strike the ground behind the airplane is called the trail, and that is shown here in the orange. If you take the trail and subtract it from the whole range, you're left with the actual range, shown here in the green, which forms the other side of a right angle triangle. This then forms a hypotenuse, which constitutes the drop angle. And this is actually represented on the Norden bombsight as its tangent, which is the opposite side over the adjacent side, or the actual range over the bombing altitude. This is the Norden bombsight disk speed control. The disk speed knob adjusts the speed of the disk speed motor here. This is the scale for the dropping angle, showing the various tangents. As you can see, this is adjusted with this knob here. The disk speed knob controlling the disk speed motor adjusted the speed of the motor for the time of fall. It required 88 1/3 turns of this motor for the bomb to strike the surface once being released. Since altitude is in feet and ground speed is in miles per hour, the conversion factor of 88/60 is used to convert mile per hour to feet per second. As mentioned, the bombsight disk speed motor is designed to rotate 88 1/3 turns from the time of bomb release to impact, and the bombsight has a constant of 5,300. If you take 5,300 and divide it by the time of fall, that gives you the disk speed setting. Conversely, if you take 5,300 and divide that by the disk speed setting, you get the time of fall. If you take the bombsight constant of 5,300 and multiply that by 88/60, you get the number 7773, which can be used in ground speed calculations. Without deriving all of the math, if you take the ground speed times 7773 and divide that by the disk speed setting times the bomb altitude, you get the tangent of the whole range. The tangent of the whole range minus the tangent of the trail equals the tangent of the dropping angle. This is an example of the bomb tables that were used during World War II for the Norden bombsight. And you can see that here at 30,000 feet with an airspeed of 200, the disk speed setting is 108.8. You can also see from the trail table that at an altitude of 30,000 feet and an airspeed of 200 miles an hour, the trail setting is 0.108. Here is a sample calculation for a general purpose 100-pound bomb, AN-M30, from the appropriate tables. We see that with a ground speed of 200 miles an hour times 7773 divided by the disk speed setting of 108.8 times the bombing altitude of 30,000 feet, we come up with a tangent of a whole range of 0.48. we take 0.48 and subtract the trail of 0.108, and we come up with a tangent of the dropping angle of 0.37. The reason this would be useful to know in advance is it would help the bombardier to rapidly set the bomb sight up before beginning his bomb run from the initial point without having to hunt around and guess at where he needed to set the disc speed motor and the tangent of the drop angle. Once this was all computed, even before the bombardier left the ground, this would then save time later on during the mission. This is an E6B flight computer similar to the one used today by pilots in training. It has multiple functions, including the ability to calculate wind speeds and drift angles, and there's a circular slide rule function as well. The United States Army Air Forces actually considered this to be the front side, with the compass rose here, and there's a table here with drift angles to the right and to the left of several airspeeds, which are shown here in 10-knot increments. This is actually considered the back side with a circular slide rule function. Again, going back to the front side, the bombardier could actually calculate the tangent of the drop angle not only for his planned altitude and ground speed, but for altitudes 1,000 feet below, 2,000 feet below, 1,000 feet above, 2,000 feet above, and also for airspeeds at 10-knot increments below and above his planned ground speed. This would allow him to rapidly perform calculations to determine the tangent of the drop angle once he knew wind speed and direction. Here you can see that the E6B has been marked with the many different altitudes we discussed: 30,000, 29,000, 28,000, 31,000, and 32,000, and all the different tangent of drop angles for different ground speeds. As you can see, this requires making about 50 different calculations. Let us assume that for the purposes of this mission, we have found out that our ground speed is not actually 200 miles an hour, but 210 miles an hour. And through using our drift meter and other calculations, we've determined that the wind is coming from 170 degrees at 20 knots. We then turn the dial here to 170, and we make a dot here 20 miles in speed from, and draw a line here. Now then, assume that our actual heading for the bomb run is 100 degrees. We turn the wheel here to 100, and we find that our arrow now and our dot have moved over here, and that our new tangent of dropping angle is 0.38. Here is now a similar problem solved using the preset dropping angle scales, although this will be from 3,000 feet rather than 30,000 feet. We see that we have the ground speed set at 210 knots, and our wind is 170 degrees at 20 knots. So again, we'll draw a dot down here and an arrow. Then we'll rotate this to the bomb run heading, which is 100 degrees. And this tells us that our drift angle is now 5 degrees to the left. Our actual ground speed is going to be approximately 204 miles an hour. And if we follow the 204 miles an hour over to the 3,000 foot line here, we see that the tangent of the dropping angle will be about 53 degrees.